Morelli.
Hello, my name is Reginald B. Little, Sr., and I'm going to talk here about recent discovery, possible discovery, room temperature, near ambient pressure superconductivity in lutetium nitrogen dope, lutetium hydride, which is a controversial topic around the world of science now. I hope by this presentation to possibly give clarity based on my hypothesis and reasoning that the confusion may be over 15 nitrogen use for synthesizing this nitrogen dope, room temperature, ambient pressure superconductor. 15 nitrogen isotope effect follows from theory of mine during the last 15-20 years of nuclear magnetic moments from certain elements having positive and or negative nuclear magnetic moments. Nitrogen is one of the unique elements of the 103 elements. It has two stable isotopes. These two isotopes, one has positive nuclear magnetic moment, the other has negative nuclear magnetic moment. And based on such drastic difference in nuclear magnetic moment, I think there's a huge isotope effect that may give clarity to this controversial nitrogen dope lutetium hydride, as I presume and speculate in my thinking that the research group at Rochester University may be doping by synthesizing with pure 15 nitrogen or enriched 15 nitrogen. 15 nitrogen is also something that I've in the last year published here at Stillman College. Recent data in collaboration with Azayo of Israel. We got data of 15 nitrogen depletion in DNA, which may give a basis for understanding genetics, developing for cancer. Also, this is consistent with recent revelation just this past week of altered DNA transcription to RNA with aging, and it's possible based on our work that with aging, redistribution of 14 nitrogen and 15 nitrogen may contribute to altered DNA transcription such that the transcription is accelerated for more error because of changes in isotopic distribution. During my time here at Stillman, I worked with a number of students. Two in particular, Naya Fowler, she's been involved in research concerning isotopic enrichment in erythritol and other artificial sweeteners, in particular erythritol and aspartame, that may explain unusual health effects of aspartame and erythritol. For example, in erythritol, in the last month, it's been determined it can contribute to blood clotting for strokes and heart attacks by ingesting erythritol in diet beverages. And we think we measured enrichment of the erythritol with heavy hydrogen, heavy carbon, heavy oxygen, heavy oxygen 17 and 18, such that based on such enrichment, the heavy isotopes cause stronger hydrogen bonding, which may explain the blood clotting. Maya Snowden is a second student. this year, we were able to get our paper accepted in helium, research done here at Stillman in collaboration with Orit Azayo. I referred to a second ago where this paper has been accepted. We give data where we measure 15 nitrogen depletion in cancer cell DNA relative to normal DNA. So these two very important topics, superconductivity and better understanding cancer, this is something that I've really contributed during the last 5 years during my time here at Stillman. But focusing more from henceforth on the superconductivity, some of the history of superconductivity. It was discovered in 1911 by Chamberlain Onnes in mercury at atmospheric pressure, very, very low temperatures, 3 Kelvin, which is about negative 270 degrees Celsius. And so since that time in 1911, scientists have been attempting to find superconductivity in other materials at higher temperature from negative 270 degrees Celsius to 0 degrees Celsius so that it may be applicable. And so since 1911, materials like lead, zinc, lead, tin, cuprates, magnesium diboride, iron oxide, high pressure hydrides recently, nickelates, and more recently this year, palladates. During this time, it's also been a great mystery to understand superconductivity and, in addition, find materials that superconduct at higher temperatures toward room temperature. A few theories have been given. One of the more successful theories, the BCS theory, explaining type 1 superconductivity. And since BCS theory, discovery of type 2 superconductivity, researchers like P.W. Anderson and Pines, they have attempted to explain type 2 superconductivity. Anderson put forth resonating bond. David Pines put forth fluctuating spin. And after these great scientists, pioneers in physics during the 20th century, Anderson and Pines, I've tried in the 21st century to develop this in a new way based on nuclear effects by these stable isotopes, which may have non-zero nuclear magnetic moments. And I proposed during 2005 that the nuclear magnetic moments may contribute to nuclear pressure for causing stronger resonating bonds and fluctuating spins of Anderson and Pines for understanding superconductivity in a new way based on the nuclear pressure from within, in addition to possible pressure, external applied pressures. And it's on this basis, this internal pressure, that I suggest may be a basis for finding materials that superconduct near room temperature at lower applied pressure, which is very important because scientists have been able to find materials that superconduct near room temperature in the last 7-8 years, but these materials require huge pressures like in the interior, the core of the planet Jupiter. And this leads to infeasibility for application. So my theory, based on the nuclear pressures, suggests that these nuclear pressures may allow lower applied pressures for superconductivity. So in these materials, hence like 15 nitrogen doped deuterium, which has a nuclear pressure, the superconductivity may occur near room temperature as well as at lower pressures, near atmospheric pressure, for applicability. And hence that's the basis for me reasoning that perhaps Ranga Dias and his research group at Rochester University may be using 15 nitrogen, and by my theory, the nuclear pressure allows them to observe superconductivity at room temperature with near ambient pressure. So, in addition to the nuclear pressure, the theory that I suggest also involve these nuclear pressures altering atomic orbitals, molecular orbitals, and band structure on the basis of the orbitals having parity of gerade or ungerade symmetry, such that the nuclei of zero nuclear magnetic moment have orbitals of gerade with balanced lobes, and orbitals of ungerade, plus and minus, also with balanced lobe, but opposite polarity, opposite sign. But the nuclear pressures distort, causing imbalance of these orbitals, which in my theory I suggest the gerade orbitals altered by quantum fluctuations from seeping of the nuclear magnetic moments may alter dissipation of the superconduction energy to thermal energy, and the alteration by the nuclear magnetic moments from the quantum fluctuations from the nuclei alter the ungerade symmetry with imbalance for pushing the charge, causing the hopping of the Cooper pairs by the nuclear pressure thereby. So in the nitrogen doped lutetium hydride, nitrogen has, like with other high pressure hydrides, a unique role. And important to point out that Ashcroft, during 1968, he gave the theory of hydrogen at high pressure behaving like a metal, and under such conditions it may become a superconductor. Then years later, he realized during the 20th century, about 2003, 2004, that chemical pressures may lower the required applied pressure for the hydrogen to become a superconductor. So hydrogen is unique among the elements, along with helium, that I put forth in my theory for explaining these properties of superconductivity of Ashcroft. The uniqueness of hydrogen and helium among the other elements, they lack core electrons, they lack core electronic shells, and even hydrogen, its most abundant element, is unique relative to helium. As the most abundant element, protium, it lacks other nucleons having only a proton. And thereby, this most abundant element of hydrogen, protium, is unique among all of the elements, which I think is contributing to this property of superconductivity, as the valence electrons interact directly with the interior of the proton. The interior of the proton being quarks, and so this makes hydrogen very, very, very unique. And one of the uniqueness by my theory, although hydrogen at low pressure will have a positive nuclear magnetic moment, under high pressures, the greater intensity of the proton interacting with surrounding electrons may use the surrounding electrons to induce negative nuclear magnetic moment of the hydride. And so this is very interesting. And it's on such basis I've drafted 3 different manuscripts. The first manuscript, I correctly assume hydrogen at low pressure, manifesting non-metal property, and its positive nuclear magnetic moment. Somehow trying to integrate the lutetium hydride with nitrogen doped lutetium hydride with other superconductors like sulfur hydride and carbonaceous sulfur hydride and lanthanum hydride. And cuprates. I revise and assume negative nuclear magnetic moment and hydride property. Now I've revised, and my third draft, I go back to the first draft as I realize that the pressure is too low, and that's actually what is wanted, is near ambient pressure. At near ambient pressure, the pressure is too low for the hydride to, the proton to induce negative nuclear magnetic moment of the hydride. And so I clarify that in my theory as far as the nitrogen dope lutetium hydride. So what about lutetium? Lutetium is a 5D transition metal, and its ion, lutetium 3+, is like lanthanide. Lutetium has 2 stable isotopes, 175 and 176 lutetium, both having large positive nuclear magnetic moments. And it is this basis of the lutetium nuclear magnetic moment that I note, as you will see, causing the nuclear pressure, contributing to the superconductivity, in addition to the negative nuclear magnetic moment of 15 nitrogen I get to here in a second, and what I just mentioned, the positive nuclear magnetic moment in the hydrogen, its protium isotope. So these nuclear pressures, by my theory, lower the needed mechanical pressure, so that, by my theory, Dias is able to see superconductivity. And the 15 nitrogen, I speculate and think, dope lutetium hydride. What about the 15 nitrogen? Well, what about nitrogen? Well, it has 2 stable isotopes, like I noted, 14 nitrogen and 15 nitrogen. These isotopes have different nuclear magnetic moments. The 14 nitrogen is more abundant, 99%, 99.63% of nitrogen by relative abundance is 14 nitrogen. Only 0.37% is 15 nitrogen. It is 15 nitrogen has negative nuclear magnetic moment. The 14 nitrogen has positive nuclear magnetic moment. And this difference in nuclear magnetic moment, by my work, my theory, causes dramatic isotopic differences and properties. So scientists trying to replicate Dias' synthesis, they are using nitrogen in its relative abundance, which is 99%, 14 nitrogen. And the resulting nitrogen dope lutetium hydride, they synthesize is enriched in 14 nitrogen and its positive nuclear magnetic moment. I think it's part of Dias's intellectual property in possible patents with Rochester University. I speculate and think they may use 15 nitrogen enriched, or nitrogen enriched with 15 nitrogen, so as to enrich the lutetium hydride with 15 nitrogen. And the resulting materials have different superconducting properties because of the different nuclear magnetic moments. And Dias synthesized his superconductor using solid lutetium and gaseous mixture of nitrogen and hydrogen with what I speculate enriched 15 nitrogen of 1% and 99% hydrogen. And the 15 nitrogen has a different nature of its triple bond. I think it's easier to break at low pressures. On the other hand, I highlight here one of the researchers in China, Wen, and his group. They used a different method to form nitrogen-doped lutetium hydride. And I think this results in different material from the original synthesis of Dias. They use a high-pressure apparatus, whereas Dias used the diamond amble cell. And they use different reactants, starting materials. Their starting materials were solid. Ammonium chloride, calcium hydride, boron nitride, and they had a gold container. So these different conditions also involve higher temperatures and higher pressures in wind synthesis. And in their material, they probably had close to the natural relative abundance of 14 nitrogen and 15 nitrogen, rather than enrichment, as Dias, I speculate, used enriched 15 nitrogen among his reactants. Therefore, the different conditions and the relative abundance of the 14 nitrogen larger, I think caused Wen to enrich his sample with 14 nitrogen. And this resulted in two different materials where the 14 nitrogen requires higher pressures and it superconducts at lower temperatures. So this has led to Wen, I speculate, inability to replicate Dias's synthesis, where I speculate Dias has enriched his superconductor with 15 nitrogen so that the 15 nitrogen allows higher temperature superconductivity at lower pressure. So this indeed is a controversy, and this controversy has exploded in science during the last 6-7 weeks, and it's led to many accusations, even some scientists accusing Dias of fraud. I don't know, I'm speculating, but I think based on the isotopes, its possibility, there may be some validity. And this is just a theory, I don't know. I haven't talked to Ranga Dias, so I don't know what he's done, but I can apply this and rationalize the possibility of isotope effect explaining what has happened. So, the 15 nitrogen, why would it cause a different synthesis relative to the 14 nitrogen? And why would the resulting superconductor by isotope effect cause superconductivity at different temperatures and pressures? Based on my theory, like I noted, the different isotopes have different nuclear magnetic moments. Different nuclear magnetic moments cause different nuclear pressures. These nuclear pressures cause different spin fluctuations, different resonating bonds for different transformation of the thermal energy and different imbalance of the orbitals by gerade and ungerade symmetries. And all of this, by my reasoning, may explain why these researchers are getting different results, and it could be based on the intellectual property and the impact of a near ambient pressure superconductor on the world economy, that there is so much secrecy, and why researchers at Rochester University is protecting some of their patent materials, intellectual property, and scientists trying to follow by what was published in Nature in March 2023 have not been able to replicate, causing all of the confusion. So, how consistent is this with superconduction of other materials? This is what I want to consider the latter part here of the talk. What I do is I note some specifics of what's going on with these isotopes in different materials, starting with the doped 15 nitrogen doped lutetium hydride, showing consistency among different superconductors and the history of superconductivity going back to ONEs on the basis of isotope effect by nuclear magnetic moment and the nuclear pressure. So in the 15 nitrogen doped lutetium hydride, during superconduction, the electron Cooper pairs colliding with atoms as they hop, as they conduct without dissipation, they cause quantum fluctuations. These quantum fluctuations are known, and this is part of my theory, they're known to spread from nanoscale to molecular scale to the atomic scale, even down into nuclei and nucleons and quarks composing the nucleons. And so these quantum fluctuations momentarily release fields on the basis of my theory from the nucleons and the nuclei, causing the nuclear pressures. And in the case of the lutetium hydride, the quantum fluctuations of the protium induce fractional fissing, quantum fluctuations of the lutetium in the material. And this induced quantum fluctuations, what I call fractional fissing of the 15 nitrogen. And this causes the nuclear magnetic moments to seep from the nuclei affecting the orbitals so as to prevent the photons from dissipating, but converting the energy of the photon frustration back into conduction so that the superconductivity can occur without dissipating the energy to heat. So just as in the 15 nitrogen doped lutetium hydride, other superconductors also, like cuprates, they superconduct by my theory based on being composed of elements having stable isotopes of both positive and negative nuclear magnetic moments. In the case of cuprates, copper, its two isotopes, 63 copper, 65 copper, both have positive nuclear magnetic moments. So the quantum fluctuations during the superconduction causing the fractional fizzing of the copper, and it induces fractional fizzing of the 17 oxygen in the cuprate. Oxygen is also an element in the cuprate. It has isotope 17 oxygen with negative nuclear magnetic moment. And the positive nuclear magnetic moment, as in the copper, its fizzing pulled the electron closer to the copper nuclei. And the fizzing of the 17, fractional fizzing of the 17 quantum fluctuations, oxygen causes it to push electrons into the copper orbitals. And these orbitals having gerade and ungerade symmetries, the gerade symmetries tend to prevent heat dissipation, and the ungerade orbitals, they tend to become imbalanced to push the charges across the nuclei for constituting the conduction. Thereby, the combined effect prevented heat dissipation with pushing of the charges across the nuclei, manifesting the superconductivity. And so the fractional fizzing of the copper and the 17 oxygen follows fusing of these, fractional fusing of these, and there's a cyclic repeating pattern of fractional fizzing, fractional fusing during the process of the superconductivity. So other materials, in addition to cuprate, like magnesium diboride, similar phenomena occur as the magnesium diboride. Its superconductivity may be understood on the basis of it being composed of magnesium and boron has two stable isotopes, both boron 10 and boron 11, having positive nuclear magnetic moment, and the 25 magnesium, one of the isotopes of magnesium, it has negative nuclear magnetic moment. So just as with the cuprates and the 15 nitrogen doped lutetium hydride, magnesium diboride also fits this general mechanism of superconductivity on the basis of positive and negative nuclear magnetic moments and their nuclear pressures created by the quantum fluctuations and fractional fizzing and fusing, inducing alterations of gerade orbitals and alterations of ungerade orbitals for suppressing dissipation of the conduction energy to heat, but by the imbalance induced in the ungerade orbitals, propelling the charges, conducting the charges, so they conduct from atom to atom without heat dissipation, hence superconductivity. Likewise, in iron arsenate, it is composed of elements having stable isotopes of positive and negative nuclear magnetic moments. Also in the high pressure hydrides, other than the 15 nitrogen dope lutetium hydride, like hydrogen sulfide, it is composed of elements, positive nuclear magnetic moment, the sulfur, and the huge pressures for it to superconduct, by my theory, induces negative nuclear magnetic moment of the proton interacting with valence electrons of hydride. So the negative nuclear magnetic moment of hydride, positive nuclear magnetic moment of 33 sulfur, leads to similar mechanism by the nuclear pressures from the positive and negative nuclear magnetic moments, for by my theory explaining superconductivity in hydrogen sulfide under huge pressures. 2 years ago, Dias shocked the world as he proclaimed superconductivity at an even higher temperature, but also at high pressure in carbonaceous sulfur hydride. And this material also explained by the isotope effect and the non-zero nuclear magnetic moments of both positive and negative natures. And so, how so? Well, we already considered the hydrogen sulfide, the sulfur hydride. What happens when you add carbon to this material? The carbon has an isotope, 13 carbon, which I think may also explain the controversy surrounding this material, like the nitrogen dope lutetium hydride, as I think the Dias group may have enriched intentionally their, and I speculate, their sample with 13 carbon. And 13 carbon has positive nuclear magnetic moment. And by the 13 carbon and its positive nuclear magnetic moment, it contributes to nuclear pressures for superconductivity at even higher temperatures than the sulfur hydride. And for this, I'd like to offer further detail. With the carbonaceous sulfur hydride, I note the carbon involves its 2p valence shell, valence subshell, whereas the 33 sulfur involves its 3p. And so this effect on subshell of lacking core, like in hydrogen, carries over for the subshell. And this is causing uniqueness of the 2p elements for contributing to superconductivity, like in the case of the oxygen of the cuprate and the nitrogen of the lutetium hydride, and in the case here, the carbonaceous sulfur hydride, the carbon. So the carbon, the nitrogen, and the oxygen, these are of the second row, the second shell, and 2p, the subshell, it lacks an inner 1p subshell. So the 2p interacts more intimately with the nucleus. So it experiences, because there's no core p. So the 2p, the elements having the 2p subshell, they experience stronger nuclear pressure by my theory here. So this is why the carbon in the carbonaceous sulfide helps the sulfur hydride superconduct at higher temperature, because the carbon uses its 2p subshell. And so lanthanum superhydride also superconducts and was discovered to superconduct near room temperature. And it also follows from the theory of R.B. Little. It is composed of lanthanum and hydrogen, two stable isotopes of lanthanum, 138 and 139. They both have positive nuclear magnetic moments. The superconductivity requires huge pressures, and this induces negative nuclear magnetic moment in the hydrogen. And so these two, they have the positive and negative nuclear magnetic moments for nuclear pressures for this mechanism of Little, explaining the room temperature superconductivity in lanthanum hydride, but requiring huge pressures. I would like to point out a recent development where scientists have been able to observe aluminum and boron nitride assisting superconductivity in lanthanum hydride, aluminum 27. And aluminum 27 has positive nuclear magnetic moment. And this follows the nuclear pressure from the aluminum assisting the superconductivity. In considering the lanthanum, I wanted to note one additional effect. The lanthanum and these heavier heavier atom superconductors like lanthanum, superhydride, they have larger atoms having larger orbitals. And the hydride, I think in my theory, by the nuclear magnetic moments, may occlude inside the lanthanum valence. In addition, these more massive, larger atoms and ions like lanthanum and yttrium, their outer orbitals have higher densities of states. So there's a possibility, like in lanthanum and yttrium, for the nuclear magnetic moments, in particular the negative nuclear magnetic moments, which tend to push electrons away from nuclei during the resonating orbitals, during the quantum fluctuations, down to the interior of the nuclei, the nuclear pressures may push electrons into these empty outer orbitals. Like in the case of lanthanum, its 4F and 6H subshells are empty. And the negative nuclear magnetic moments of the hydride at the high pressure may push electrons, by my theory, into these empty orbitals, which may be a basis for this superconductivity. And so this is a new idea that I put forward, further explaining the superconductivity mechanism. And so likewise with yttrium superhydride, It is a high temperature superconductor under high pressures. Researchers were shocked because they expected yttrium superhydride to superconduct at higher temperature than they observed. Somehow it didn't conform to conventional electron photon theory. And I would like to put forth this as support to my mechanism of the nuclear pressures from the nuclear magnetic moments, because in the case of yttrium, its nuclear pressure arises from it having negative nuclear magnetic moment. Unlike the other superhydrides, the element other than the hydrogen had positive nuclear magnetic moments, but 89 yttrium has negative nuclear magnetic moment. And because of this, by my reasoning and my theory, I can explain the discrepancy by the conventional electron-photon interaction in the yttrium superhydride. Recently, it's been discovered that doping the yttrium superhydride with 105 palladium helps the superconductivity at lower pressure. And this is consistent also. So I emphasize all the consistency because I feel it gives more validity to my theory of the nuclear magnetic moments and the nuclear pressures. It is not coincidental among all these materials. I can rationalize the superconducting behavior by the nuclear magnetic moments, positive and negative. And palladium has isotope 105 having negative nuclear magnetic moment. And it's on this basis, the negative nuclear magnetic moment allowing the superconductivity at lower pressure in the yttrium superhydrides. So, in addition to these materials that I pointed out, and I picked those materials because they follow a trend. I had another slide here, but it didn't copy. They follow a trend of increasing temperature and lower pressure from the mercury to the lead and tin to the cuprates to the magnesium diboride to the iron arsenides to the high pressure hydrides, trend of increasing critical temperature during the last 115 years, and lower pressure towards ambient pressure with the revelation last month of the nitrogen dope, the controversial nitrogen dope lutetium hydride. But there are many other materials of lower critical temperature that I note in the next 3 slides that also follow my model. Materials discovered to superconduct but at much lower temperatures, like manganese bismuth compounds, niobium sulfur compounds, cobalt indium compounds, uranium telluride compounds, rhodium arsenide compounds, platinum phosphide compounds. All of these materials composed of elements having positive and negative nuclear magnetic moments. And by my theory, nuclear pressures can explain the superconductivity, although the critical temperatures are low. these high entropy materials, having rhenium, niobium, titanium, zirconium, hafnium. Recently in 2019, zirconium iridate was observed to be a superconductor. Barium, titanium telluride, ytterbium, rhodium silicide, indium 10, all of these materials having elements which have stable isotopes of positive and negative nuclear magnetic moments, and my theory explaining their superconductivities, although at much lower temperatures than the 5 or 6 that I highlighted. The theory is explaining, my nuclear pressure theory is explaining the superconductivity in these materials. And I think this empowers my theory, and I think scientists around the world, based on what I'm presenting here, may take a stronger interest in my theory, these materials here also. So with this, I will conclude. The sulfur hydride under high pressure has been accepted by the scientific community as a high temperature superconductor. The lanthanum superhydride has been accepted. The carbonaceous sulfur hydride has been a controversy during the last 2 years. And what I'm saying here, maybe that controversy is because of 13 carbon. And scientists have not been able to replicate because they have not enriched their carbonaceous sulfur hydride with 13 carbon. And just this week, aluminum was observed to dope and assist lanthanum superhydride in its superconduction. But in March of this year, Ranga Dias report nitrogen-doped lutetium hydride. And for the last 7 weeks, 8 weeks, scientists have not been able to replicate. And there's controversy and speculation of data manipulation and fraud. I don't know, but based on my theory, possible isotope effect of 15 nitrogen, I think that Dias may synthesize his compound with pure 15 nitrogen or 15 nitrogen enriched nitrogen for 15 nitrogen doped lutetium hydride. And I think if other scientists attempt to replicate using 15 nitrogen enriched precursors, this would test my hypothesis. With that, I conclude.